Yesterday we defined this new concept of electric field as a region in which a force could be experienced by something with a charge. It's kind of like a gravitational field, right? There's a gravitational field that surrounds the Earth of about 9.81 meters per second squared, depending upon where you are on Earth. Well, we invented the idea of gravitational fields to help us to understand gravity without having the need to have something experiencing gravity. I've got a board marker in my hand right now. If I drop that board marker, it accelerates downward at 9.81 meters per second squared. We say the gravitational acceleration, or sometimes the gravitational field, is 9.81. But if I don't have it there, if the board marker isn't accelerating, it doesn't mean that gravity has disappeared. The Earth that's causing gravity is still there. So how do we describe that gravity? We don't have a force anymore because the board marker's gone. We describe it in terms of these fields, these gravitational fields, this region in which a gravitational force could be experienced by something with mass. We have the same idea with electricity. If we have a charge producing something, a charge affecting something else, that something else would experience a force. But if we take that something else away, the bigger thing that was causing it hasn't disappeared. So this electricity hasn't disappeared either, but we no longer have a force. So we have to describe it in terms of fields. An electric field is that region that surrounds a charged object where we could experience an electric force if there's something there to experience it. But remember that if there's nothing there to experience it, the field is still there. It's just there's no force if there's nothing there to experience it. They surround electric charges. Okay? They surround producers, or electric charges. They are vector fields because they have a direction associated with their influence. And if I have a positive thing that's causing a field or a negative thing that's causing a field, they affect things differently. So there is a direction associated with the influence, as opposed to, say, something like a light field that influences us and travels in a certain direction, but doesn't influence us in a certain direction. So we call those scalar fields. We said a minute ago that fields exist as long as there's a producer. Now we can have two types of producers, unlike with gravity. The only type of producer we have is a mass, right? Positive mass. But with the electricity, we can have a positive producer or we can have a negative producer, two types of charges. Those fields exist as long as we have that producer, regardless of what kind of producer it is. A force, on the other hand, only exists if you have something causing it, but also something experiencing it. So let's go back to gravity for a second and the board marker. The Earth produces the field. The board marker experiences the field. Whether the board marker's there or not, as long as I have just the Earth, I've got a field. But in order to have a force, I have to have the Earth and the board marker, something to produce it and to experience it. So force, you got to have field and, force, you have to have a producer and experiencer. And field, all you need to have is the producer. Could have the experiencer as well, but you don't need the experiencer. Now, let's get into the nitty-gritty of this. We defined yesterday the direction of the field in two ways, similar to the way we define the direction of the field in gravitational fields. In gravity, we'd say the field would point the way that a mass would move if placed in the field. Here's my marker. Drop the marker. Which way does it move when placed in the field? Down. So the gravitational field is down, the way that the marker moves when placed in the field. Well, we also say that the gravitational field points toward the Earth. Well, electric fields, we define them, though, as the way that a particle would move, well, specifically a positive particle would move if placed in the field. Let's say we got a positive producer here. Okay, that's what's caused. This would be analogous to the Earth causing gravity. Okay, my big positive producer. Let's say I have a little positive experiencer over here placed in the field that surrounds that positive producer. Which way is it going to move? Which way is the force on that positive experiencer over here? Outwards. It's away from this guy, right? Going to go this way. Therefore, we would arbitrarily define the direction of the field as to the left at that point. Now, what about this? What if this is a negative particle? Which way is the force going to act on it? It's going to point towards it. Does that mean the field is towards it? Not at all. The field, represented by the purple there, is outwards or to the left at that point because that's the direction that a positive would move if placed in that field. But here, we would say the field is still outwards because even though we have a negative there, that's the way that a positive would move if a positive was there. Now, let's look at this one as a negative particle. Let's say that this is positive again, this is negative. Which way is the force on the positive right here? To the right. Which way is the force on the negative? Outwards, like up and right. Which way is the field right here? To the right. Quinn? Yeah, good. Which way is the field here? Inwards. The way that a positive particle would move if placed in the field. We've got a little expression to help us remember this, okay? We're going to say the force is with the field. The force is with the field. Are you sure the force is with the field? I'm positive the force is with the field. I'm positive the force is with the field. Okay? Whenever we have a positive particle, the force is with the field. I'm positive the force is with the field. If we have a negative particle, the force is against the field. Make sense? Force is with the field right here because it's positive. The force is against the field right here because it's a negative particle. That's arbitrary, right? Somebody sometimes said, listen, we're going to define the direction of the field as the way that a positive particle would move if placed in the field. Could we have defined it opposite to that? The way that a negative particle would move? Absolutely we could, but we just didn't. So we got to go with the convention so that everybody's speaking the same language. It's the way that a positive moves when placed in the field, or the direction of the force on a positive when placed in the field. All right, let's draw a couple of diagrams here. Let's say we got the first one is a positive particle. Field goes. Remember, we define it not only as the way that a positive moves when placed in the field, but away from the positive toward the negative. Field would go this way, right? And we could draw a bunch more field lines if we want to, but don't really need to. They're all pointing away from the positive. This one's negative. Which way are they pointing? Inwards, towards the negative, right? Because if I put, notice, I don't have an experiencer here, I just have the producer. But if I did put an experiencer here and it was a positive experiencer, it would experience a force toward the negative. Therefore, since we define it as the way that a positive would move, it's inward, toward the negative. What if I made these close enough where they interacted with each other? What if we made this a positive particle, this a negative particle? Well, away from the positive and toward the negative. Oops. That's not toward the negative. That is toward the negative. Notice that these field lines end up joining up. That's what the electric field will look like between a positive and negative. Remember this, please. When a field lines join up, we would say that there's a force of attraction. You can see that these two objects would attract each other because one's positive, one's negative, right? There's that force of attraction when the field lines join up. Versus if I had a positive and a positive right here, these two guys are going to produce fields that look like this. Field lines go away from the positive, right? Notice what happens when they get close to each other. The field lines repel each other like this. They don't join up. When we have field lines that don't join up, we find that they repel each other. Now, you look at these two situations without the field lines drawn, easy enough to tell they attract and repel, right? Listen, I can guarantee you on your next unit test, and I can virtually guarantee you on your diploma exam, that you're going to get at least one question where you have diagrams for either electric or magnetic fields. And you've never seen magnetic fields yet, but they're not all that different than electric fields, actually. You're going to get one of those on your diploma exam, almost certainly. And it may be a diagram that you recognize, just like I've drawn up here, and you got to determine whether they attract or repel or something like that. Or the diagram may be completely different. They may come up with some wacky diagram with 3 charges in crazy positions. Do they attract or repel each other or whatever? Here's the rule. If the field lines join up, if the field lines join in the diagram that you're given, then they attract. Doesn't matter what the diagram looks like. If the field lines join, then they attract. If the field lines don't join, then they're going to repel each other. Sometimes it's not as easy to determine as it is in these 2 diagrams whether we have attraction or repulsion. And by the way, how would I make this one? How would this one be different if I had made them 2 negatives instead of 2 positives? Shirley, what would be different about this? Not much, but what would be different about it? If these were 2 negatives down here. Yeah, shape would be the same, right? It would still be repulsion, but this time we would have the fields going towards the negatives instead of away from the positive. All right, in this one, we did this yesterday in the recording as well of class. We said that if we have if we have a positive particle here that's at rest, it experiences a force which way? Don't remember? The force is with the field, right? Right? Right, Justin? Are you sure the force is with the field? I'm positive the force is with the field. So the electric force would be downwards on this. What if we had a negative particle over here? Which way would the force be? Well, we don't have a nice way to remember this, but it's opposite positive. So the force has got to be opposite the field. What if the particle was moving to the right instead of stationary? Which way would the force be then? Still down. What if this one was moving to the right? Force would still be upwards. What would the shape of this path be? This is like throwing a ball through the air. Okay, it's moving to the right, but it experiences a force downwards. What's the shape of the path when a ball moves to the right and experiences a force downwards? It's a parabola. So it would end up looking like this. This would be a parabola as well, except it would be a parabola upwards like this. What about this one? What if I had a positive moving downwards? Which way is the force? Downwards. What if I had a negative that's moving downwards? The force would be upwards. So if that particle was moving downwards, it would end up slowing down, right, as a result of that upward force. Okay? All right. That's the qualitative nature of electric fields, at least to the detail that we need to know them. We finished off yesterday by talking about the equations of electric fields and relating them to gravitational fields. First one isn't even really fields, it's actually force. Gravitational force between 2 objects with mass, gravitational or electric force between 2 objects with charge. Coulomb's law, right? We spent a couple of days on Coulomb's law last week. It's the last 2 that I really want to focus on. Gravitational field is Gm over r squared for a producer. Electric field is Kq over r squared for a producer. So if you know something about the producer, what causes the field, use this equation to find its value. And finally, gravitational field experiencer. E would be equal to F, not over M, but F over Q. Now, I like to put absolute value signs around there. Although if you forget, I can live with that. It's not a big deal. What I can't live with is if you forget to put the vector sign over top of it. I promise you, if you do not put the vector signs over top of it, if you skip the vector sign, it might not seem like a big deal, but I guarantee you, every single one of you in this room, some point this year, will get electric fields mixed up with energy. At some point, you're going to set energy equal to electric field, and that's wrong. You can never do that. But if you call it E without the vector sign over it, you're going to do that. All of you. Now, if you put the vector sign over it, it helps you to remember that there's a difference, right? And even if you do that, you still might make that mistake and set them equal to each other. But you're less likely to make that mistake. Some of you will do that when we put the vector sign over it. All of you will do it if you don't put the vector sign over it. Sum is better than all. All right. Yesterday we saw an example question with some follow-up questions on worksheet number 8. We'll give you some answers to those, and then we'll take a look at the ones that we need to go over here. All right, then. We'll take a look at number 2, 3, 6, and 7. 2 says find the field strength and direction of the field 300 millimeters to the right of a negative 2 coulomb electric charge. We're going to find the value of that field by saying KQ over R squared. Listen, this charge is a producer, so let's find the field caused by a producer. It's 8.99 times 10 to the 9 times the charge, which we're going to drop the sign of the charge. Oops, just 2, I guess. It is important what the sign of the charge is for determining direction, but not the magnitude here. R is 300 times 10 to the minus 3, or 0.300. Do the math there. It works out to be 2.00 times 10 to the 11. Now, what about the direction? Let's draw it out here. Here's a negative charge. We want to find the field strength to the right of it. Okay, which way does the field point? Which way does the field point when you're to the right of a negative? Points to the left. Good, man. Matt, how do we define the direction of the field? Is the force with the field?
Yes, the force is right. No, the force is not with the field.
Are you sure?
Because it's a negative, so no.
Yeah. If we got a positive particle, it is, because I'm positive the force is with the field. But if it's a negative, the force is against the field. Therefore, if we put a positive particle right here, okay, sorry, a negative, what do we got here? Yeah, if we put a positive particle right here, the force would be with the field, which would be pointing to the left there, towards the producer there. Yep.
Is the R supposed to be in centimeters?
No, it should be in meters. So 300 millimeters is 0.3 meters divided by 1,000.
Makes sense.
Yeah. So this is going to be to the left. Does that make sense? 2.00 times 10 to the 11 to the left. Now, number 3 says calculate the strength and direction of the field 8.5 centimeters to the left of this electric charge. Once again, 8.99 times 10 to the 9 times Q, which is 300 times 10 to the minus 6, 300 microcoulombs, divided by 0.085 meters, gives us a value for electric field in number 3 of 3.73 times 10 to the 8. Now, what about the direction? We get a positive charge to the left. Field points away from the producer, right? Toward a negative, away from a positive. So it's going to point to the left again. Okay, Kelly, is that okay? Nick, is that okay? So for question number 2, Nick, the field pointed toward the negative producer. And number 3, the field points away from the positive producer. So because it's the opposite side, it's pointing to the left still. Okay? And what do we have, 6 and 7, was it, or 5 and 6? 6 and 7? 6 says calculate the magnitude of the field experienced by an alpha particle, and what's the acceleration? Here's the force experienced, and here's the charge of the alpha particle. By the way, you probably don't remember the charge of an alpha particle, so where are you going to find it? On our data sheet. It says plus 2e, right? And e is the elementary charge, so it's twice the 1.6 value. Do the math there. E works out to be 6.25 or 625. Want to find the acceleration? Remember what needs to be with you to find the acceleration? The force needs to be with you to find the acceleration. Then what do you do with the force? Sorry? Right. F is equal to m times a, or a is equal to f over m. Take that value that we just found, divided by the mass, which is 6.65 times 10 to the minus 25, which is also where? On your data sheet, yeah. And you're going to get a big acceleration here, 3.01 times 10 to the 10. Would this value be bigger or smaller if this was an electron? We're using an electron instead of an alpha particle. Bigger acceleration, smaller acceleration? Bigger? Who said bigger? Okay, Cole, how come it's bigger? Right. Same force. Actually, it wouldn't be the same force because the charge would be different. But let's assume that we had the same force. All right, with a smaller mass, we're going to get a bigger acceleration. That's like Newton's second law that I taught literally just this morning in Physics 20. A is equal to F over m. You push on a smart car with a certain force. You push on a semi-truck with the same force. Which one's going to accelerate more? The smart car, right? Because it has less mass. Same force, less mass, more acceleration. And finally, 7. Calculate the magnitude of the net force experienced by an electron if the electric field is 1.0 times 10 to the 3. We're going to say E is equal to F over Q. We're going to rearrange it. Now, did anybody think when they saw this question that maybe we should try F is equal to KQ1 Q2 over R squared? That's not invalid here, but it's not very helpful. Like, we don't even know if we have, we don't know anything about the producer, what its charge is. If we did, then we could use KQ1 Q2 over R squared to find the force, but we don't. All we have is the charge of the experiencer, which we're dropping the sign of, and we have the electric field strength experienced, 1 times 10 to the 3. So we get a force that's 1.6 times 10 to the negative 16 newtons. I think that's what I got. Yeah. Is that okay?